Good morning, students. Today I am going to solve the exercise 1.1 of the first chapter, real numbers. The first question is use Euclid's division algorithm to find the SCF of two numbers. The first part is 135 and 225. Now, first, you know Euclid's division algorithm is A equal to BQ plus R, where A is the dividend, B is divisor, Q is quotient, and R is remainder. And you also know A is always greater than B. So first I am dividing the greater number 225 by smaller number 135. So when we divide 225 by 135, the quotient is 1 and 135 1 ja 135. Now the remainder is 0, 90. And here you can see this remainder is less than the previous divisor 135. So then 135 comes here. Again we'll divide 91 ja 90. Now the remainder is 45. Now again you can see this remainder is less than the previous divisor 90. So now I will divide 90 by 45. 45 to the 90, and here you can see the remainder is 0. This is the flow chart, and here I am going to write the algorithm A equal to BQ plus R. So one more thing, this is the sign of division. This dividend A comes here, divisor is B, quotient is Q, and here after subtracting this is the remainder. So these are the signs. So here first A is 225, second A is 135, third is 90. First B is 135, second 90, and last is 45. The first quotient is 1, second is 1, and last is 2. Here I am going to write first A is 225, and for that B is 135 into Q. First Q is 1, quotient 1, sorry, plus remainder R is 90. Now second A dividend is 135, for that divisor is 90, Q 1 plus its remainder is 45. Now last A dividend is 45B, quotient is 2, and the final result is, now the remainder, here the remainder is 0. So now the SCF of these two numbers is 45. This is the answer. Now one more example, the second part of the exercise. Here two numbers are 196 and 38220. Again the same method, first I am taking A is the larger one, 38220, and B is 196 because A is always greater than B. So first I am doing the flow chart. 196 and the dividend is 38220. The first 196 and 382 1 sorry. Now the remainder 6 8 186 and 2 is there. So here you can see this first remainder is greater than 196. So here we have to divide again. 196 9 ja 9 6 ja 54 9 9 ja 81 9 1 ja. Now the remainder 8 9. Now again we have one more digit here. So again you can see this remainder is greater than the divisor. Again we have to divide. 196 5 ja 980. The remainder is 0. So here you can see we have first dividend is 38220 and divisor is 196 and the quotient is 195 and remainder we get 0. So now here again I am using Dirichlet's division algorithm. A equal to BQ plus R and B is 196 Q is 195 plus remainder is 0. So now we got the SCF of these two numbers is 196. So this is the answer. Now C part is homework. Now you will try, and the numbers are 867 and 255. Now the question number 2 is show that any positive odd integers is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integers. And before that I want to tell you that if we divide any number, the number is 7 by any divisor, suppose the number is 4. So you can see 4 1 ja 4 and the remainder is 3. This is less than the divisor. तो आप देख सकते हैं कि अगर मैं 7 को 4 से डिवाइड कर रहा हूँ तो रिमाइंडर क्या आएगा 3. Similarly, if I divide 9 by 7, the remainder is 2. So here you can see now if you don't know the numbers, if I am dividing any number by any other number, then the remainder is less than this divisor. This is B. ये क्या होते हैं, B से छोटा आएगा हमेशा. तो वे राइवल लिमिट्स R or maybe 0 or 1 or 2 or 3 or 4 or means less than B. Here you can see divisor is 4 and the remainder is 3. So means for if I am dividing any number by 4, possible remainders are 0 or 1 or 2 or 3, means less than divisor. So we will use this funda here. Here the question is 6q plus 1 r, means 6q plus 1 here, or 6q plus 3 or 6q plus 5. We have to prove these all are odd numbers. Means if I compare with Euclid's algorithm, this is A equal to BQ plus R. So by comparing, you can see B is 6. And if B is 6, possible remainders are less than 6, means 0 or 1 or 2 or 3 or 4 or 5, less than 6. Now A can be, or A equal to B is 6 Q plus R. First R is 0, or BQ plus R. Second R is 1. PQ plus R. Third R is 2. Or BQ plus fourth R is 3. BQ plus R. Fifth R is 4. Or last is 6Q plus R. R is 5. So these are the algorithm. Now finally, here the question is odd integers. Odd integers, here 6q plus 0 is not an even odd number. So first is 6q plus 1, odd number. 6q plus 2, then 6q plus 3, odd number. 6q plus 4 even, 6q plus 5. So this is the answer. Now question number 3rd. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to match in the same number of columns. What is the maximum number of columns in which they can march? So you know, if I give an example, suppose in an assembly the students are standing like that. Then in the assembly, answer says equal at the last. So what will you do? So just you will shift these students from here to some students to this line, this row, and some to this row. So this, then finally we will get this format, equal at the last, means number of columns and number of rows are equal. So for that, in mathematics we just find the SCF of these two numbers. Now the same rule you can use Euclid's algorithm. A equal to BQ plus R. You can do this. Now question number 4. Use Euclid's division lemma to show that the square of any positive integers is either of the form 3m or 3m plus 1 or for some integer m. So here you can see the square of any positive integers. So for the question is we have to prove 3m or 3m plus 1. Here if I take b as 3, you can see possible remainders are, for 3 possible remainders are 0, 1 or 2. Now I am using Euclid's division algorithm. A equal to BQ plus R. Now first one, B is 3, Q plus R. First R is 0. Second, A is 3Q plus R. Second R is 1. And last, A equal to 3Q plus R. R is 2. Now the question is square of positive integers. So first I am squaring both sides. Same here and same here. So you can see a square and here 3q plus 0 whole square. A square is 9q square, and here we have to prove this one is in the form of 3m. So for making 9q square in 3m, first we will take 3 as common. The remainder is 3q square. Now how it will become 3m? So for that we have to suppose this 3q square as m. So it becomes 3m. Now first part is proved. Now second. Again here squaring both sides. A square is now 3q plus 1 whole square. So now a square is a square plus 2ab plus b square. Now here the answer is 3m plus 1. So how we'll make this 3m plus 1? So 1 is already here. So for making 3m here, take as 3 as common, plus 1 is here. Now 3q square plus 2q. Now for making this 3m, we have to suppose as this as m. What? 3q square plus 2q is m, suppose. Now this becomes 3m plus 1. This is proved. Now the third part, again squaring both sides. It becomes a square plus 2ab plus b square. Now because the answer is 3m plus 1, how we can get 1? So we'll break this 4 is as 3 plus 1. 3 plus 1, 4. And here 9q square plus 12q. For making it 3m, again we'll take 3 as common, plus 1 is here. Now it 3 3 ja, 3 4 ja, 3 1 ja. Again it for making it 3m, so we'll as m. it becomes 3m plus 1. So this is the proof. Now next day we'll start next exercise. Thank you.